In this video, we're going to look at some properties of acids and bases. So I'm going to test some things, and a couple things we can do is, first off, over here on the left, I have some sodium hydroxide. And then over here in the middle, I have some hydrochloric acid. And on the right, I have some sodium nitrate. So I think we're going to look at these paper tests first. And here I have a red piece of litmus, which is more pink, a blue piece of litmus, and then a piece of pH paper. So what I'm going to do here is put a drop of this base, NaOH, onto the pink litmus paper, and let's see what happens to that. Okay, that is turning blue. I'm going to put it on the blue litmus paper. And that looks like it's just staying blue. And then I'm going to put it onto the universal indicator. It looks like I spilled a drop already. And you can see that. And that's getting to be a dark blue. So these two are litmus papers right here. And the pink turns blue and the blue stays blue. What I have here is a universal indicator. And we can look here. It looks like it's really dark. Like, I don't know, 12, 13, and 14 all look really, really dark. So it would have a real high number. Let's just call it 13, but somewhere in that range. And that would be the pH of that substance. Okay, I already put drops on here. On the pink litmus paper, it stayed pink. On the blue litmus paper, it turned pink, and you can kind of see it's gradually, as it's getting moist, it's moving up and turning more and more pink. So this is the hydrochloric acid, and it's turning both pink. And then the hydrochloric acid is an acid, so it's on the opposite end of the scale. And I don't know, it looks like a 1 or a 2, or probably a 1 or a 2, probably closer to a 1. That we'll call that a really dark red that we have right here. The sodium nitrate was the third thing, and that one has kind of the pink stayed pink and the blue stayed blue, and the pH paper didn't change much. It stayed in there right about, I don't know, about 6, 5, 6, 7. Ideally it would be neutral, it would be 7. However, carbon dioxide gets in from the air and probably makes it slightly acidic. So I'd say it's more like a 6 about looking at the color of that. So those are some papers, either litmus or pH paper, and the pH paper is actually a combination of indicators giving off a wide range of colors like this. But you can see it for these three substances here, the sodium nitrate over on the right, the hydrochloric acid in the middle, and the sodium hydroxide on the left. There were a couple other tests where I put 10 drops of a substance in a test tube, and to this one I'm going to add some cabbage juice. So I'm going to put a couple drops of cabbage juice in here, 2 or 3, and this is actually red cabbage juice. Okay, so we start out with a clear solution. I'm going to do it in the HCl as well. And then I'm going to put it in the NaNO3, and we'll take a look at the 3 different substances. Okay, so I do that, and this one turns green. So the base turns a tealish green, probably more of a greenish green in that case. This one turns kind of a rosy pink, the acid, and then the neutral one just kind of stays the purple color of the drops that I put in. Doesn't do much. So the red cabbage, in a base environment, it's more of a green. In the acid environment, it's more of a rosy pink. And then in a neutral environment, it doesn't change much. One other thing is I'm going to use phenolphthalein. This is often used in titrations. And I'm going to put 1 drop of this in here. This is the NaOH. 1 drop in the HCl. And 1 drop in the neutral substance. Okay, and notice it gets very pink. Okay, actually 1 drop is a very concentrated amount. So the base turns pink. And the acid, it might be getting cloudy just because it's so concentrated, but it doesn't turn pink. And the same thing with the neutral one, it doesn't turn pink. It might be cloudy just because it's so concentrated right there. Don't know if I showed you that good enough. So that's the one that turned cloudy. that turned cloudy, but still clear, or still no color. And then this one turned getting my shadow in the way here. I want to avoid that. That one's definitely turning pink. All right, so those are just some tests that you can see. And what we went through, I'm going to move some of these things to the side and maybe look at our chart. And we kind of funneled some things into all the acids. If we look at this chart right here that we have, sorry about that. We'll get this going. And all of the acids we're going to see have, they're red in both characteristics, they're clear. For phenolphthalein, they have low pHs below 7, and they turn pink with the cabbage juice. Okay, notice all the acids have acid in their name, and they have this H plus ion in all of them, and they're able to release that. If we look at the bases, which are sodium hydroxide, we're going to see typically an OH and an OH, and you're going to get higher numbers of pHs, and it's teal, probably more of a green right there when we look at the cabbage juice, and we notice that the pink litmus turns blue. Now notice we do have one more base here, which doesn't really have an OH in it, but it definitely is a base, and we're going to learn a little bit more about that when we look at our characteristics right here. So finally, I'm just going to look at some characteristics of acids and bases based on what we saw earlier, and just lining them up. Litmus, acid turns red or pink, bases are blue. Phenolphthalein, the acid is clear, or you might have saw that cloudiness, but it's not pink, the bases turn pink. The pH of an acid, and we're going to learn more about that scale, is less than 7. Bases are greater than 7. We saw that with the numbers on the pH paper. Pink in the cabbage juice for acids, more of a teal or green for the bases. We're not going to taste these, but acids tend to taste sour, like lemons and limes. Bases like soap would be bitter. Bases generally have a slippery feel. You can think of that with soaps. Both of them are electrolytes. They break into ions and conduct electricity. So both acids and bases are electrolytes. Acids dissolve in water to furnish H plus ions. Bases dissolve in water to furnish OH minus ions. That's a core definition. I don't want to say a basic definition because acids are involved too. We can expand that definition to say acids are H plus donors, okay, which is really the same as dissolving in water to furnish H plus. But now we can say a base is an H plus acceptor. Would OH minus accept an H plus? Yes, because OH minus and H plus would form water, which would be a neutralization. And then an even broader definition we won't do much with is a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor.